The video I featured today is not a music video, right? It's a collection of sudden damages of bridges due to different reasons, right? So far we have talked about, in chapter 2, we have talked about how to design simple structural elements based on strength criterion. Okay, and this videos just show you why we need to do the designs and how important a good design is. Okay, in chapter 2, we just talked about those simple concepts, and later in this semester, in the following chapters, we will start to look at specific structural elements, like axially loaded elements, torsional elements, and beams. Okay, we will learn how to analyze the stresses and calculate the deformations of the structural elements. So today we will start to talk about axially loaded elements, and we will introduce how to calculate the deformation in axially loaded elements. And the core equation is just given here, as delta is the deformation equals FL over EA. So I will show you how this equation can be derived. So in chapter 2, we have talked about the thermal effect on deformation. Right? We have introduced the thermal effects and how can we consider it in structural analysis. Right? So basically, the thermal effect can be described by two equations. Right? The first one is the thermal strain. Right? Thermal strain equals alpha times delta T. Right? So it's important to know that the delta T is positive when you heat it, and it's negative when you cool it. Right? The alpha is CTE, right? Coefficient of thermal expansion. And if we want to know the deformation, it's just strain times L, the original length, right? Or alpha delta T, original length. Okay, we give several examples about how to use these two equations to calculate the thermal effect. And we also introduced the basic design concept and how to design a structural elements based on strength criteria. Okay, I have given several basic examples, and I also uploaded a integrated example. Right, that is our example 4. I hope you have gone through this detailed example. And some students have emailed me telling me that you have troubles understanding part of the steps of example 4. So let's go through this example 4 together briefly. Okay. So in this example 4, we have a bridge. It doesn't matter how big this bridge is, but we just need to know this bridge uses kind of cable connection. Okay, and this cable connection is shown here. You can see that this cable connection has several parts. Okay, if we want to determine the maximum allowable force that can be carried by the connection, we have to know the stress that can be generated in different parts. So you can see that in this connection we have 3 parts basically. It's shown here: gusset plate, cable connector, and bolts. Okay, so this plate is called gusset plate. It's just a plate connected to the support and with 2 holes on it. Okay, it's a plate with 2 holes on it. And we can assume that this is a rigid support. Okay, then we have this cable connector. Well, these 2 things are cable connectors. It's just a connector with 4 holes. Right, it's connected to the gusset plate through 2 double shear bolts. Okay, so the third part of it is just bolts, the 2 double shear bolts. Okay, you can see that we can simplify this problem into the 3 parts, the 3-part gasset plate, cable connector, and bolts. So the critical part of this problem, of this example, is to analyze the 3 parts one by one and find out, based on the given questions, given conditions, what are the maximum loads that you can apply to this connection. Of course, we assume that the force is applied to here, right? Let's give it F, then it will be stretched. Then different parts of this connector, of this connection, will be loaded, and you can see what kind of stresses can be generated in each part of it. Let's look at part 1, the gasset plate. As I said, this gasset plate is just this white-colored plate. Well, this is a typical problem in chapter 1. Okay, when you have such a plate with 2 holes on it, and you're loading it in such a way that F is applied to here. So what kind of stresses will be generated in this plate? Okay, we have 3 basic types of stresses: normal stress, shear stress, and bearing stress. Okay, do we have normal stress? Do we have bearing stress? Do we have shear stress? Okay. So if we have all of them, where we have the maximum values of the stresses. Okay. Obviously, in this gasset plate, we only need to consider normal stress and bearing stress. So where you can find the maximum normal stress? Right, just where you have the smallest cross-section area. Right? And in one of the examples in chapter 1, we said that in such cases, the smallest cross-section area just appears where just going through the center of the hose, going through the center of the hose. And where you have the bearing stress, right? The bearing stress is just on the upper edge of the hole, right? Upper edge of the hole. And the interface between the bolt and the gasset plate are just two semi-cylinders. Right? As we said, we don't need to consider the whole area, the whole interface area. We only consider projected areas. Right? So the projected areas will be 2 rectangles. Okay, then you can calculate the 2 cases, right? Just normal stress and bearing stresses, and compare them with this yield stress with factor of safety. Then you can determine 2 maximum forces that are allowed in this system. Okay, you got the 2F values. Then in part 2, the cable connector. But here this is the cable connector. Again, do we have normal stress? Do we have shear stress? Do we have bearing stress? In this case, we have to examine the normal stress and the bearing stress. Okay, so the normal stress is here, right? Just as shown here, this is normal stress, where the normal stress will be generated. Okay, just in this cable connector where you have it's a ring. So originally it's a ring. Right? So you have 2 rings, but you have another 2 on the back side here, right? On the back side, because those are the double shear connectors. It's shown here. This is one side, the other side. Okay. So basically, if you want to know where is the smallest cross section area, just here, right? Again, going through the center of the hose on the connector. So you just get here just a 1 rectangle minus this hole of the connector. You get an area. We have 1, 2, and on the back side 3, 4. Right, and multiply it by 4. You get the overall cross section area carrying the normal stress. Right. So you can calculate the normal stress and the bearing stress. Where you have the bearing stress? This time, since you add the F here, so the bearing stress will be here. Right? Again, you only need to calculate the projected areas. You get one area, multiply it by 4. Right? Then from step 2, you can get another 2 F values. Right? Then in step 3, we examine the bolts. The bolts only carry shear. Right? So we have to examine the shear stress. So just surfaces, the cross-section area is 1, 2 on the back side, 3, 4. Okay, you just need to get these 4 areas and calculate the shear stress. So finally, you can get how many F values? 5 of them, right? So you need to select the smallest one to limit the overall loading as the maximum allowable loading in this connection. So in the gusset plate, as we just analyzed, you have to divide it into 2 steps. In the first step, you examine the normal stress. Second step is bearing stress, right? And the key is the most critical step is to find the correct cross-section areas. Right, so in this first step, normal stress of the gusset plate, as we mentioned, the cross-section area is just this long rectangle. This is the cross-section of the gusset plate, and you have 2 holes. Right, so you reduce these 2 holes. Right, minus these 2 holes, so you get the cross-section area. Right, so the overall size is just WT. Just here is 18. The thickness is 2. Right, and here the diameter of the hole is 3. Right, so basically just 18 times 2 minus 2 times 3, and you have 2 holes times 2 again. So you get a 24 inch. Then you just F over area, you get an expression of the stress, and then compare it with the allowable stress. Okay, just as the yield stress over factor of safety. Then you can get an F value. That is 517 kips. Okay, so to examine the bearing stress, again, you just need to find out the cross-section areas. As we mentioned, you just need to consider the projected area. Right, just the hole, the projected area, it's just thickness times the diameter of the hole. Right, it's just the same as here. Right, 2 times 3. Then you have 2 holes and times 2. You get 12. Right. So then from here, again, you just need to compare it with the yield stress over factor of safety, and you get another value. Right, this is half of the previous one. So in the cable connector, again, it's just as we mentioned, you have 2 steps: normal stress and bearing stress. Right, to calculate the normal stress, we need to find out the smallest cross-section area. Right, just as we analyzed, it's just here, it's just a 1 cross-section area, and you multiply it by 4. Right, here it's just it got a smaller rectangle minus a hole. Right, so that is the diameter of the ring times the thickness minus diameter of the hole times the thickness. Right? You get 6. Then you have 4 of them. Right? So 4 times it, you get 24. Right? So we get a expression f over this a. Compare it has to be not higher than the yield stress over factor of safety. Then you get a value, the f value. So here you have a different yield stress and different factor of safety, because it's a totally different parts where you may have different materials. For the bearing stress, as we mentioned, the bearing stress is here. Right, so just a projected area would be just the diameter of the hole times the thickness of the connector, right? Diameter of the hole times the thickness of the connector. And you have 1, 2, and backside 3, 4, right? So times 4. You get a cross-section area, and repeat the process F over A, not higher than yield stress over factor of safety. So you get the force F. Okay, then in the part 3, we're analyzing the bolts. Okay, the bolts, as we said, it only carries shear. So we have the cross-section area. This is one circle, 2 circle, and on the back side 3, 4. Right. So you have 4 times 1 cross-section area. One of them is pi d squared over 4. Right. Then you get the area, and the F, of course, here is V equals F, right? So F over the cross-section area is not higher than the allowable shear stress. Okay, you get to the 5th. This is the F5, right? We have this 5 calculated F values based on different conditions. Right here, we just need to determine which one should use as the maximum allowable force. Okay, obviously the minimum one, the smallest one, should be used to limit the overall load applied to this system. Okay. That is the last one.